Okay, so let's start this next set of lectures. So it's by Professor David Dean from University of Bordeaux. So he's going to teach us stochastic density functional theory of interacting Brownian particles. Is it? Yeah.
Right. I haven't changed the program. Yeah, so thank you very much for the invitation. It's nice coming back to the ICTS and seeing the gardens have grown so nicely. So yeah, so I'm going to start, I'll start here where the board's dry. So I'm going to give lectures on stochastic density functional theory. Actually, I have to write bigger. It's basically, what is stochastic density functional theory? We're going to look at interacting particle systems, and we're going to, so in principle, these systems are described by a set of stochastic or Langevin equations. And what we're going to do is we're going to take these Langevin equations, and a bit like you do with the Boltzmann equation, Fokker-Planck equations, we're going to write down an evolution, we're going to look at evolution equations for the density field, and we're going to use those evolution equations to study some physical problems, okay? So in order to do this, there are basically 4 chapters. There are lecture notes which I will distribute at some stage when I'm sure all the mistakes have been taken out of them. So the first chapter, what I'm going to do is I'm going to look at stochastic calculus. In fact, Ito calculus and Langevin equations. So this might be revision for some of you, but it's very important for the development of the theory. Okay, so I'm going to talk about Ito calculus, which is a form of stochastic calculus that we use to do this SDFT. There are other forms of stochastic calculus. I won't go into them. I might mention them briefly. So this is your physicist, okay? So this isn't going to be rigorous mathematics. It's like, you know, it's like the Australian cricket team playing cricket, okay? There's a bit of cheating will go on. But hopefully the spirit of, well, not even the spirit of the game is preserved by the Australians. But hopefully I'll try and sort of explain how you might make things rigorous, okay? Okay, so I'm going to start off. What I'm going to look at is discrete time continuous stochastic processes. What I'm going to do is I'm basically going to construct Brownian motion. Okay? So what I write down, so actually I always think it's a good idea when you want to look at something mathematical. When I was a student, I did maths. I didn't really like programming or anything like this, but actually I realized as I got old and grey that actually a way of making sure what you're doing is well defined mathematically is to think, how would I do this on a computer? So what we're going to look at is I'm going to construct a stochastic process. I'm going to have some sort of time intervals. I'm going to have a time interval delta t, okay? So I'm going to have some time n, this is time n plus 1, and this interval length here is delta t, okay? So what I write down, I want to write, so I have times which are discrete, they're given by n times delta t, where n is an integer, okay? So now if I want to write down a difference equation, on a computer if you want to solve an equation, you're going to look at you have the process at the time n plus 1 times delta t. Okay, so this is the step xn plus 1. Let me just write it as in a differential form. So this is minus the position at the earlier time, n delta t. So I'm going to write this is equal to u. And look at, it's going to depend, this velocity will depend on the position at time n times delta t, previous time. So now we multiply that by delta t, yeah? So you can see here, if I divide by delta t, this is going to become the time derivative. So this is imagine you have some sort of random particle in a river. So imagine the river has a local flow u. So it's basically being, it's drifting in the flow of the river, okay? So this is called an advection term. And u is some sort of fixed deterministic function It can depend on time, but I won't make it depend on time. Now what I want to do is, so I'm going with the flow in the river, okay, but there's also some molecular diffusivity, okay, so there's some sort of Brownian motion within the flow. So I'm going to have something, right, a of x of t. So this is a deterministic function. I'm going to multiply this by a random number, delta b of t. So delta b of t is the randomness, okay? So what I'm going to do to construct, so this is a Gaussian random variable. So the first thing, if I'm a Gaussian random variable, I need to know which of its moments, how many moments do I need? It's a Gaussian random variable, I only need to know its mean, so I'm going to take delta bt to be equal to 0. If it didn't have a 0 mean, I could have sort of included it as part of the deterministic drift. And I'm going to take the delta bt squared is equal to delta t. So that looks a bit strange. So what it means is that morally, this term, delta bt here, is square root of delta t. Okay, so this is one of the important points in stochastic calculus. So if you want to write down the probability distribution for this object here, so the probability that delta b is between x and x plus dx, that's equal to p of x, little p of x dx, p of x is equal to, so if I write down, this is the standard formula for Gaussian random variables, so you have delta t is the variance, I have exponential minus x squared over 2 delta t. So it looks like this. So if I'm doing this on a computer, what I would do is I would fix my delta t, and when I wanted to calculate delta b, I would take the square root of delta t, then I would call the routine Gauss dev, which gives me a random variable, Gaussian random variable, which has variance 1. And so I would take delta t, square root, times Gauss dev of idem, okay? And that will generate it. And you put that on a computer, and it will generate your stochastic trajectories. Now, the other thing which is important is that this noise has no memory. Okay, so if I look at delta b of t, delta b of t prime. So these are the discrete times. Okay, so this guy here would be n times delta t. This guy here would be n prime times delta t. This is equal to 0. Okay, so this means that on the scale you're looking at, the collisions, the molecular collisions have a very, very short time scale. Okay, so there's no correlation between these noises. Okay, so let me have a look at the simplest case. Okay, we know what this term u is doing. We know what. So let's have a look at the case where we just take u equal to 0, and let's just look at what this process here is. Okay, if we take the delta b of t's. So if I set the drift equal to 0, okay, and what we're going to do is I'm going to take a to be a constant. Okay, so I'm just looking at the simplest case. So my difference equation now is x of n plus 1 times delta t minus x of n times delta t is equal to a times delta b of t. Okay, so that equation I can actually solve easily. Okay, I can just sum it up, and what I'm going to find is that xn of delta t, which is equal to x of t, my notation, is equal to, so I have to have if I have a starting position at x0, okay, so I have the starting position, and then all I've done is I've added up these Brownian increments between times I equal 1 up to n, of a factor of a in front, and I have my delta B. It's the noise at the time, I delta t. Okay, so this is my stochastic equation. This is the integrated equation. So the interesting thing is, now I want to know what's the probability distribution for the process x of t. Okay, so what does it look like? So the easiest way to work out the probability distribution is, instead of looking at the probability distribution, I look at its Fourier transform. So I say that Px of t is the probability distribution function of x of t. Now, if I define its Fourier transform, p tilde k of t, that's equal to the integral dk exponential minus ik x times p of x dx, okay? But actually, this is also the characteristic function. I mean, I'm just, because I'm integrating, sorry, dx, because I'm integrating the probability distribution against this exponential here, I'm just computing the expected value of e to the minus ik of the random variable that I'm interested in, okay? So this is what I'm interested in. And so when you can see, this process is constructed by adding up independent increments. So actually, things always simplify. It's a shame we don't have periodic boundary conditions on this blackboard. No, it would make the lecture much good. Okay? So you've got this. So I want to compute this Fourier transform. So this means that p tilde of k, am I writing big enough? Is it okay? Yes, okay, good. P tilde k of x of t, this is equal to, so it's the expected value of, so I can take, if I look at what the, if I look at what this guy here is, I mean, I have the x of 0, okay? So I can take out e to the minus ik x of 0 here, okay? So that's just the constant term. And then I have the expected value, the expected of e to the minus ik a times the sum of these b, delta b, delta t, I delta t, okay? Is equal to 1 up to n. Okay? Now the thing is, these guys here are all independent random variables, and they're identically distributed, okay? So I can write this as e to the ik x0, then I just get e to the minus ika delta, I can write down any of these delta b, okay? I've dropped the index I, and I'm going to have n of them. Okay? And if I use this, if I just do the Gaussian integral here, you can check it, it's very easy to do. This is going to give me e to the minus ik x0. If you work out this is just going to give you the e to the minus k squared a squared over 2 times delta t, right? If I work out what this integral is here using the formula for Gaussian integral, and I've got a factor of n here, so I'm going to get just n times t. So this gives me times t, okay? Now that looks like something you've probably seen before. If I invert the Fourier transform, what you basically find is there's an a squared here. It's a Gaussian, right? So it's the solution of the diffusion equation. So actually the process that I'm constructing at these discrete times actually solves the diffusion equation, okay? So it actually solves this equation. So it's just a solution of this. Okay, where d, So let me see. So it has this form here. It's the solution of a diffusion equation. You see the initial condition is that Px of 0. If I put that means I start off at the point x0. And what you find is that d, the diffusion constant, is equal to a squared over 2. Okay, so when you write down the diffusion constant, normally what you have is you have a 4 pi dt here, okay? So this is this is the effective diffusion constant. Or this is the diffusion constant. Okay, so a bit later on I'll say, well, actually when people first wrote down the diffusion equation, they didn't do stochastic calculus, did they? I mean, they used Ficks Law, and they talked about, so you take Ficks Law and you talk about the conservation of particles, okay? So that's, normally it's derived phenomenologically. So this is a description in terms of paths of what the stochastic process which generates, which is described by the diffusion equation, okay? So the other thing is if you define the displacement in time t, if I define delta x is equal to, so delta of x is equal to x of t minus x0, okay? So this is if it starts off at x0, I'm looking at how far it diffuses, finishes off at x of t. You can see that if I calculate the characteristic function of that, the term here, x0, cancels, and I find that the expected value of e to the I k delta of x of t is just equal to e to the minus d. I used the formula for a squared was 2d, so I find e to the minus k squared d times t, okay? If I Taylor expand that exponential, this is equal to, so let me do the Taylor expansion in terms of k here. So this is how you use a generating function to compute moments, okay? So this thing here is just 1 plus ik delta x of t minus k squared over 2 delta xt squared, etc., etc. And so let's have a look at this. This is 1 minus d times k squared t. So we can see that if we compare the powers of k, well, the ones are okay. This means that there's no power of k on the right-hand side. So that means the expected value of delta x of t is 0. That's just because the increments were designed to have 0 mean. So I find that is equal to 0. And I also find that, so if I compare this, this tells me that delta xt squared is equal to 2d times t. Okay, so this is the way we talk about the diffusion constant in terms of the mean squared displacement. Okay, and when physicists always have this factor of 2, and mathematicians tend to have a factor of d. So what we've constructed, so this looks like a promising way of looking at things. So now what we want to do is we're going to, you know, as the Australians would do, we're going to take the limit delta t goes to 0 in a completely unethical way. So we're going to look at the Stochastic Calculus. So when I first started doing this sort of stuff, I used to work with mathematicians. I actually wrote some papers with mathematicians. And we tended to get the result quicker than they did. So we'd do look at a calculation, we'd get the calculation, and then we would say, well, yes, you know how to drive the Ito car, but do you know how to fix it if it breaks down? And we used to say, no, but we can drive the Ito car at 180 miles an hour on a country road while drinking a beer and smoking a cigarette. Okay? And every now and again, we would break it, which was fun. Okay, so now here we want to take the continuum limit. Okay? So what I'm going to do is, and this is a very important point actually. The whole of the stochastic density functional theory relies on the trick that I'm going to show you. It's quite an incredible property of continuous Brownian motion. So let me look at S, which is equal to the sum I is equal to 1 up to n of delta bi squared. You'll see why I'm looking at this. I always hate this when lecturers used to say, consider the following, and then they would derive something, but this is the way it works, okay? So let's have a look. So let's have a look at this random variable. So the expected value of S is equal to just take that inside the sum. So this is equal to times delta t, because dbi squared, they're just equal to delta t. So this is just equal to n times delta t, okay? And let me call that t. Okay, so I'm basically looking at what this sum, the idea is what I want this to become some sort of integral. I want this to start looking like an integral, okay? So S, the average value of S is equal to that, so that's fine. Now let me compute its variance now. So what I want to compute is, let me look at this S squared, okay? So if I want to compute S squared, what I have to do is I have to take 2 copies of this guy. Okay, so I'm just writing, I have a double sum here. So I'm going to write this as d delta bi squared delta bj squared. Okay, and I have to take the average value of that. So if I say Wick's theorem, and you've heard of it before, put your hand up. Okay, so I'm going to use Wick's theorem here. So Wick's theorem basically says that when I look at zero mean Gaussian random variables, okay, what I do is I basically look at all of the possible ways to pair them, okay? So and I take the average. So this is the sum I is equal to 1 up to n. The sum in the lecture notes I've actually explained Wick's theorem in a bit more detail. So actually there are 2 things I can do here. What I can do is actually I can decide, so I have to choose, put these guys in pairs. So what I can do is I can take the delta bi squared, okay, and put the 2 delta b's together, okay? I can also take the delta bj squared, okay? But actually I've got 2 factors of delta bi, so when I decide to cross the I and j, there are actually 2 ways of doing it. So I get a factor of 2 here. Okay, the j's here, each of the j's here, I can decide to put the first j with the first I. Okay, so this is 2 times, so I can write this delta bi, delta bj. Okay, and so I have factor of 2 of these guys, okay? Okay, so this is this is what I've got. So I have to be careful in my sum now because actually, so all these terms here are never 0, right? So what I find here is I have the sum of I equals 1 up to n, the sum of j equals 1 up to n. So delta bi squared, so that just gives me delta t. Delta bj squared, that gives me delta t, so that just gives me delta t squared here, right? Now when I look at this other sum, I have a factor of 2. But if I is not equal to j, it's 0, okay? Because I said that they had to be independent. So now, so I have the full double sum here, but here I just have the sum. Let me just call, so I have a delta ij here, okay? So I have the sum I is equal to 1 up to n of 2 times, so this is just, so when I is equal to j, this is just delta, this is just going to give me delta, sorry, the 2 is here, so this is going to be delta t squared. Does everybody agree with that? I wasn't looking at my notes when I was doing it. Okay. Okay, now let's have a look at this. So if we look at this, you can see that, well, the delta t squared is common to everything. So this is going to give me delta t squared, and there are n squared terms in the double sum, yeah? Okay, and then the second term, well, here we're going to have we just have 2 times n, because we don't have the diagonal term times delta t squared, okay? Okay, so if the total time is t, this is now equal to, so delta t is t divided by n, so this gives me t squared divided by n squared times n squared plus 2n times t squared over n squared. So this is equal to t squared plus 2 t squared over n. Okay? So this means that, so if I'd already calculated the average value of S, so you remember the variance of S is equal to the expected value of S squared minus the average value of S all squared. So you can see that this term here is going to cancel with this term here. So we're actually going to get, this is equal to 2t squared divided by n. So if I go to the continuum limit, that means that n goes to infinity, okay? What I actually find is that the variance of S goes to 0. Okay? So what do you call a random variable with variance 0? Is it an interesting random variable or is it a boring random variable? It's a very boring random variable, okay? It's basically, so you basically have a random variable which is equal to its average value with probability 1. Right, you think about the formula I showed you for the Gaussian. This term here was the variance, right? This is the term, this term here is what you call sigma squared here, okay? Sigma squared here. And obviously, as sigma goes to 0, that becomes a delta function, right? So a deterministic random variable, something which isn't random, actually has a probability distribution. It's just that it's a delta function. Okay. So we have this is going to 0. So now I'm going to write down the continuum limit. Continuum SDE is just, so I just write it dx of t. Okay, what I'm going to do is so delta t is going to become dt. So the part which was deterministic, okay, just going to find ux of t dt, and the part which is random is going to become, write this as ax of t, and I'm going to write the infinitesimal limit as dbt. Okay. If I look at this formula here for s, which was equal to the integral of db squared, the integral of delta b squared, in the continuum limit, this integral is basically the integral between 0 and t of db of s. S is the time variable, okay? Squared. So S is, okay? And what I've shown, okay, is that this object here is actually equal to its average value. Okay? And dbs squared is just equal to ds. Okay? So if I take the derivative of that, ds by dt. So that's equal to dbt squared. Just, okay, this is just db times db. I'm just using this notation, so you're not, that's just equal to dt. So it's strange. So you have something which is a random variable, db. Okay, it's a Gaussian random variable. But in the limit of in the continuous limit, dbt squared is not actually a random variable. Okay, so this is the point about the Stochastic calculus. So that's completely non-rigorous, okay? And you probably induce a few heart attacks in the mathematical community, which would at least, create a few openings for younger people. But there we go. But anyway, that's the cheap and cheerful way of getting the Stochastic calculus. So I haven't finished yet. What I want to do is now, it's Stochastic calculus, okay? So now what I need to do is to define differentials within the stochastic calculus. So let me take some function f of x of t. Yeah? S is the integral of z. Yeah. Let me see, wait a minute. Yeah, but it is dt. No, but yeah, it's dt. This is equal to t, right? So when I take, sorry, it's ds. Okay, sorry, that's... Okay, so the rule in Ito calculus is that what happens in Ito calculus stays in Ito calculus. No. The rule in Ito calculus is that you never divide by dt. If you're a mathematician, once you will divide by dt, okay? Because we're not afraid, basically. Okay, but the mathematicians, they never divide by dt because the noise becomes something horrible. Okay, so this is the main point. So let me have a look. Let me take some function f of x of t, and let me remember that the stochastic differential equation I was interested in is dx of t is equal to ux of t dt plus a x of t dbt. So I'm interested in that. So let me just look at the morals of what's going on in this equation here. Let me just, you can see that this term here is order dt, the first term, the drift term. And the term here is of order dt to the half, because we said that dbt squared on average is equal to dt, okay? So morally, dbt is of order delta t to the half. So now if I want to, so this is a function of this trajectory. Let me look at the derivative. So this is, I increase the time step. Let me look at df of x of t, okay? So as usual, the derivative, the differential is defined as f of x of t plus dx of t minus f of x of t. Okay? So this is equal to, so what notation? So this is equal, so let me do a Taylor expansion, okay? Let's just, this is df by dx, evaluated x of t, times dx of t, right? And normally when you do differential equations, okay, the first term cancels off, and normally when you do differential equations, you stop there, right? Right, and you divide by dt, and then everybody's happy. But the point is that, let me just, for the sake of fun, just let me keep the second derivative term. Okay, so that's evaluated at x of t, and you have dx of t squared. So when you're doing, normally when you're doing differential calculus, dx of t squared is never survives, right? It's always thrown away. Yes? Of course it's risky. Yes. But it works. Okay? So we're expanding a function. The function itself has to be continuous, right? The jumps in the stochastic process can be a bit nasty, but the function itself is okay. So what we're doing is the function has to be smooth, okay? But not necessarily the increments of this process, right? But don't worry about such things. We're here to do physics, okay? So now what you find is, so let me have a look. So the thing is, normally you throw away this, okay? The sad dx squared is normally thrown away like some unwanted Australian cricket captain. And so now, but we're going to keep it because you can see now dx of t, so let me write the first term. So this is, we have df by dx times dx of t. So we have our equation u of x of t dt plus a x of t dbt. So that's fine. So this is of order, this is an important term, right? We can't throw this away for the moment because this is of order dt. This is the most important term. This is of order dt. But now when we look at this dxt squared term, actually, see if I take this and square it, well, I'm going to have u squared dt squared when I square that, right? But that's dt squared, so you can throw that away because I'm only looking at this to order dt. I can look at the cross term. There's a cross term which is ux of t, a of x times 2 times dbt. But if I count the powers, that's dt to the power 3 over 2. Okay, so he can go away. But I actually have this last term. So this last term is the most important term. And this is a squared of x of t times dbt squared, which is of order dt. But now the important thing is we know that this is equal to dt with probability 1. So this is basically equal to df by dx times u of x of t dt. So that's just... And so this last term is the Ito term. Yes, times I've forgotten the second derivative. Okay, so we have a slightly different form of calculus. So there are other forms of stochastic calculus, which I might mention later on, but we'll use the Ito one. There are actually formulations where we actually recover the usual rules for calculus. That's called the Stratonovich calculus. And that's used by mathematicians when they want to look at diffusion on manifolds. It's a more convenient way of looking at it. But the Ito calculus is the one we're going to stick with. There's even an anti-Ito. Okay, so this is the first thing. So this is the basis of the... Okay, so now let me take the average of this equation. Okay, so let me look at the average value of df of x of t. So actually what happens now is, you can see that this term here, db of t, is independent of x of t, okay? It doesn't matter, it's just pulled out of the computer independently of what we were doing. So when I take the average value of this thing here, let me do it in 2 steps. So this is equal to, so I have df by dx of u. Okay, this is all evaluated x of t, so I have the average value times dt. And then this second term, you see, it looks as if a db of t, okay, plus okay, and that's times dt. But the point is that this is depending on x of t, okay? The dbt is drawn out of the computer at the next step for the evolution. So actually what I can do here is I can actually say, well, these two, basically what that means is these two guys here are independent. So when I calculate this average, it's actually evaluated x of t, but this is just the average value of dbt. So this guy here is equal to 0. So actually what I find, and what I can do now is I can divide, because I haven't got b of t anymore. See, if I divide dbt, which is of order delta t to the half, by dt, it's 1 over delta t to the half, right? And so when I take the limit, it's not nice. But so you don't talk about things that are embarrassing. It's a bit like an English family. So I can divide by dt. I can take it inside the expectation because the expectation is linear. So this is just equal to, so let me write everything out explicitly. This is df by dx of x of t times u of x of t. Well, I can just add this on, plus a half. Okay, so the average value, and actually what's important actually, when you do stochastic density functional theory, and we'll come back to this when we derive it, you can see probably those of you who've done the Fokker-Planck equation, we're going to end up deriving the Fokker-Planck equation from this formalism. Actually, the secret of stochastic density functional theory is not to throw away this term. Okay, so when we repeat this sort of calculation in the next lecture, I'll be hanging on to that term, sort of keeping the fluctuations. See what that means. So let me see. And so now I'm going to talk about the generator of this stochastic equation. Yep. This here. So it basically means that when I constructed my process in a discrete way, I assumed that dbt, right? So I have x of t. Okay, so I have x of t, and dbt I just get out of the computer, so it's completely independent of x of t. Okay, so it's just 0, right? So they're just independent. Okay, actually when you do the Stratonovich calculus, actually, the dbt isn't actually completely independent of the previous x of t. But this is a very important point, okay? This is crucial, okay? That there's no correlation between dbt and the time that you're currently at. Okay, so let's have a look at the next thing. I want to talk about the generator. Okay, and the forward Fokker-Planck equation. Okay, please let me know if my writing gets smaller as I go on. Is it all right? It's still big enough? So we get a piece of chalk which is a bit longer. Okay. So let me think of some sort of function, right? I have some sort of function of a stochastic process. Let me have a look at f. Some function of my stochastic process, f of x of t. Let me just denote here. So the problem is, so this has little x of 0. So this is the average value of a function f of x of t of my stochastic differential equation, given that I start the process at t equals 0 at x equals 0. Okay, so it's just a way of denoting this is the initial condition. So this thing here just means that x of 0 is equal to x0, okay? So if I know the probability density function, right? So I have so in principle I have I can say, well, I know how to compute this. This is just I want to calculate the average value of some function f of x, right? I take the probability distribution to be at x, given I started at x0, okay? So this is the probability density conditioned on starting at x0, and I have to look at the time t. Okay, so I just integrate over all the values. That's the expected value of fx of t. Okay, but I don't know yet what the probability distribution function is. What's the initial condition on this PDF is, of course, that's equal to delta of x minus x0, okay? So that's just a definition, right? So now we're going to use the Ito formula. I mean, there are lots of things that actually become very, you play around with Ito calculus, and there are lots of things that there are ways of deriving Fokker-Planck equations with Onsager-Maklub expansions and things like this, but lots of things which become slightly easier when you do the Ito calculus. So what I want to look at, sorry? Oh, where t equals 0, yes. Okay, thanks. That was df, yes, but what, did I not divide by dt? Oh no, I haven't I did, yes, so sorry, okay. So where did I, I'm getting lost. Someone can navigate for me, please? Okay, this is it, okay. So this is the equation I want to use, okay. So, where am I? Okay, good. So if I use this formula, I also have, so if I want to calculate, so I can just take the derivative inside here, okay? So df by dt of x of t, given I started at x of 0, if I look at this equation here, this is equal to f of x, and then the derivative goes here, okay? So this becomes dp by dt. I should use a partial derivative probably, okay? So this becomes dp by dt of x0 of t, okay, dx. So that's just from my definition here, right? But now I can also use my Ito formula over here, and this says that it's the expected value of this stuff here, okay? So if I want to compute the expected value of that, what I do is I say, well, I want to calculate the expected value of that. So I take px of t, px(x0) of t, I integrate with respect to x, the function which is here. So it was u of x, okay? Okay? So actually what I can do is I can write this is equal to dx px of 0 of t. And I can actually say, well, this is a differential operator acting on f, right? So I can say this is equal to some operator g acting on f of x. So g is called the generator. And in this case here, g is equal to what? G is just taking u of x, it's taking the partial derivative with respect to x, and it's also taking this a squared x over 2 times d2 by dx squared, okay? So I look at these two formulas and I think, well now, you see, f is here, and I didn't really say what f was. If we want to quibble, we want something which probably has derivatives that exist, okay? So it has to be reasonably smooth. So I have the f here, and I have the derivative here. So what I can do is I can just use the definition of the adjoint operator. So the definition of the adjoint operator, this is an inner product, okay? So instead of having the g acting on the f, I can bring it round here and make it act on the p. So integration by parts, basically, okay? So this becomes the integral df of x, the adjoint operator of g acting on p, x of x0 of t. And it's acting, this is an x operator, okay? So this operator g, just so you don't get confused, x is just the, x0 is just the initial condition. This guy is acting on this x here, okay? x0 is just being sad, left alone, nothing's happening to it, okay? So this is my form. Now the thing is, if I say this is basically true for any f, which is reasonably smooth, I can just read off, so this guy here must be equal to this guy here. So I find the Fokker-Planck equation. So the forward Fokker-Planck equation this means that it just means that this is acting. I mean, the definition of the adjoint is that, well, this is the definition of the adjoint, okay? If I have two functions, little f and g, yeah, I mean, yeah, it's acting, if you like, yeah, it's acting on the right, but what I'm doing is I'm moving it to the left, so it looks like this. Yeah, it's the Hermitian. Where? Oh, that should be dx. Okay, so is everybody right with that? So you can see that, so if I look at this f of x, so here we have f of x, which is more or less as arbitrary as we would want, and we have this yellow guy here, and then we have this blue guy here. So the blue must be equal to the yellow, and that's basically just the Fokker-Planck equation. The Fokker-Planck equation is telling you that dp by dt is equal to g dagger p. Okay? This guy here. So this equation here, if I take the derivative with respect to t of this equation, you see, this guy, the f, doesn't depend on t, so the t is here and he gets differentiated, right? Do you want to hear a bad joke about partial derivatives? So the exponential of x lives in a forest with all the other functions. And one day he's going to school, and his mother says, look, there's been a letter from the school. There's a bit of a problem. There are derivatives who are running around the forest causing trouble. And so the little exponential of x says, okay, I'll be careful on the way to school. So the exponential of x, he's walking along the path and he gets to the bridge. And sitting on the bridge, there's this nasty-looking differential operator, okay? And the exponential of x says, can I go across the bridge? And the differential operator looks at him and says, yes, but you'll have to let me differentiate you. Okay, so the exponential x, he thinks, well, differentiate me. He says, I'm going to go. He says, I'm the exponential of x. You won't do anything to me. So the little exponential actually goes across the bridge, and he's differentiated upon, and he disappears. And the derivative says, he didn't realize I was d by dy. So okay, so bad jokes. Okay, so that's the forward Fokker-Planck equation. So now so all we have to do is work out what this adjoint operator is. And so basically all we've done is I've just done an integration by parts that instead of acting on f, I make it act on p, right? So we can actually see, so basically what happens here. So if I look at g dagger, if I want to compute g dagger, then I take two functions. The definition of g dagger is that, so f, if I take little g of x, and then g of f of x, right? That is equal to okay. And it's very easy. Who can tell me what g dagger is equal to? So g dagger is, so if I ignore if I assume that the probability distribution is going to 0 at infinity, or I have periodic boundary conditions, I ignore the boundary terms. So you can see that g is, so this guy here I only have to differentiate once. So g becomes, but he's going to change his sign, so I'm going to get minus d by dx of u of x. Okay? So let me write it on a test function. Okay, so that would be equal to that times f. And then the other term, I have to integrate by twice, if I have to integrate by parts twice. So I get a plus sign because I do it twice. I'm going to get a half okay? Is that fine? You can do it as an exercise or ask me in the examples class later in the tutorial. So this basically tells me that my Fokker-Planck equation is dp by dt is equal to, so now I have to just put p here so I can write it, normally you write the first derivative term twice. Okay, so that's the Fokker-Planck equation. Okay, so it's so you can see this is the usual term that you have for convection, right? If you write down a convection equation, if you have some particle which has a velocity field u of x, you find that. So that's a quick way of getting the Fokker-Planck equation. So actually, how do we do this in higher dimensions? Which this guy here. Oh no, yeah, it's just the my d's they change randomly. Yeah, I should have written a partial derivative here, yeah? Here. This should be a partial derivative. Okay. So let me see. Okay, so that's good. So that's the Fokker-Planck equation. I don't know. Okay, so I play around the it's quite a quick way, no, of getting the Fokker-Planck equation. Who thinks it's a quick way? Who thinks it's a slow way? Okay. Okay, so normally, so let's have a look at what happens in higher dimensions. This is very easy to extend. play exactly the same game. Okay, so now what I'm going to do is I'm going to write my SDE in terms of vectors. So I'm going to write that dx of t is equal to u of x of t dt. And actually a sort of common way of constructing the noise is to write it in the following form. Take a matrix. So let me see. So sorry, I have to write in indices. So this is dxi of t. Okay, so I is the spatial index. Okay, so dxi of t is equal to ui of x of t plus aij x of t times dbj. So I'm sort of generating a Brownian motion by multiplying it by some matrix aij. So I'm using the summation convention, right? So if I have two indices which are the same, it means I'm summing over them. So this is matrix multiplication. So that's the general form for a stochastic differential equation in d dimensions, right? Okay, and what you do is, I mean, there are lots of different ways of defining the noise. So in this case here, the dBIs are independent Brownian motions, or independent Brownian increments. Okay, so basically this means that dBi, Ito rule becomes dBi, dBj is equal to, again we find it's dBi, dBj, do the calculation. And that's equal to dt, but only if I is equal to j. So I have a Kronecker delta here, okay? And so if you want, so that's my Ito convention. And if I want to find the Ito rule, then I just use the Taylor expansion for a function f of x with a little increment y. So this is just equal to f of x. So when you do the Ito calculus, you have to take the second derivative into account. So this just gives you df by dxi, dxi. Then you have another term here, which is a half d2f by dxi, dxj. And then this gives me dxi, dxj. So I have to keep, when I use the Ito rule here, I have to use this. Okay, I have to keep this term here. And so this actually gives you a generator g of f, which is equal to a half aik of x, ajk of x. So it's like multiplication of the matrix with its transpose. The second derivative d2f by dxi, dxj. And then you have the other term, which is just u of xi, ui of x, df by dxi. So that's all easy to show. It's a trivial exercise from what I've shown you before. Okay, so that's the generator. And so you get the Fokker-Planck equation by calculating the adjoint. So the d-dimensional Fokker-Planck equation becomes dp by dt is equal to d2 by dxi dxj aik ajk divided by 2p. And then you always have this usual, the drift term, okay, which is the term. That's the d-dimensional Fokker-Planck equation. Yes? Sorry? I'm just looking at for general. Oh, sorry. Yes, I'm sorry. This should be yi here. Yeah? Sorry, this is. Okay. Well, actually, what will happen, as long as the noise is Gaussian, right, and as long as it exists, okay, then you can always write it that way. Yeah, just you can basically. So it's, it's just easier to do things that way. But I could have basically defined a noise with. This is the correlation function of the noise, right? The correlation function of the noise. I could have defined a process with a correlation function, which is the matrix A times the transpose of the matrix, okay? Okay, I could have done that, but you can see, basically what I'm doing is, this has to be, this, so you can see that this matrix here has to be, it's symmetric, right? So it has to be positive definite, because it's a correlation function for noise, right? So if you give me a reasonably well-defined correlation function, in general, I can write it in that form now, okay? There might be some sick counterexamples, but in general, that's no problem, okay? So that's the stochastic differential calculus. Has anybody heard of Stratonovich calculus? So Stratonovich calculus, what would happen is that one of these derivatives would move through, okay? So you'd have a derivative here. And have you heard of, and that's because there's a correlation between the noises at different times. So there are two ways of seeing it. Either you can say that there's a correlation with the dBIs, or the function, the key thing is this A. This A, what's important is in Ito, this A is evaluated at the early time. In other forms of the calculus, this A can depend on the next variable, okay? So you can have Stratonovich calculus, you can have Ito calculus. So in Ito calculus, all of the A's, imagine I have A squared, all of them are here. And I can actually start moving them through. If I take one of the A's and put it past the first derivative and leave it here, that's Stratonovich calculus, okay? And there's another calculus which is called anti-Ito calculus. I'm not quite sure. It wasn't developed by a member of the family of Ito, but it's anti-Ito. And basically in anti-Ito, all of the A's move outside, okay? But the last derivative, everything has to be inside the last derivative. Why? Nothing goes past the d by dxi because you have to have conservation of probability, okay? So it has to have a form. Your Fokker-Planck equation has to look like a divergence, okay? So when you integrate over all space, you want this to be 0, okay? So this last d by dxi is always there, you see. Okay, so we're going to use the Ito calculus, which is obviously the easiest one to implement on a computer as well. So that's in my lecture notes. I have brief words about stochastic calculus. Okay, so where am I? Here. So let's have a look at an example. Now, actually, this is what I've been constructing, the basic process. If I look at this stochastic process, dx of t is equal to dB of t, or a multiple of dB, that's a mathematician's Brownian motion, but it's not the same as a physicist's Brownian motion. So 1.6 is physicists. 1.5 was a brief word on stochastic calculus. Okay, 1.5, Stratonovich, anti-Ito, and sort of the whole continuous family of these. Okay, so 1.5 is well spotted, man. Okay, so let's have a look at physicist's Brownian motion. So actually, physicist's Brownian motion is not what we were looking at. Okay, we're talking about positions, and actually, a physicist's Brownian motion is basically based on the idea that a particle has a certain velocity v, it's in a fluid, and if it moves with the velocity of v, there's some sort of friction. So let me write down Newton's second law. So the equation is, so we have the actual process, dx of t, actually, that's its velocity, okay? That's just a definition in stochastic calculus language because I'm too scared to divide by dt. This is just the definition of the velocity. So So I have a m dv of t. So I want to write down Newton's second law, right? So this is the acceleration. So I want to have some sort of frictional force, right? Some sort of damping due to the liquid, okay? And I want some sort of noise. Well, I don't know what sort of noise I want. I'm just going to write some constant because I'm a times dB of t, okay? So this is the frictional force on the particle. This is the drag, if you want. No? Oh, yes, dt, sorry. You have to remind me to put the dt's in. Okay, and this is sort of molecular noise. So it's not the position. It's not the position of the particle which is Brownian motion, and this isn't strictly Brownian motion. This, okay. So this is mdv. So this is what's called an Ornstein-Uhlenbeck process, but in the velocity space. Okay. So let's have a look. So let's have a look if we can solve this equation. So this is just Newton's second equation. Okay, that's a bit of noise. So let me see. So now I want to know what's A. How do I construct A for my particle? Okay. So let me have a look. Let me have a look at. So let's have a look. For instance, we know that gamma for a spherical particle. Okay, in a liquid viscosity. Eta, we know the friction coefficient, we have that Stokes tells you that the friction is equal to 6 pi eta times r, right? But r is the particle radius. So basically this calculation is very complicated if you look at most textbooks. So this is the viscosity, r is the particle radius. I left a gap here. Spherical something particle in liquid of viscosity eta. It has to be solid. So it has no slip boundary conditions. If you have a liquid which has the same viscosity but doesn't mix with the other one, you have a factor of 5. And if it's an air bubble, it's 4. Okay, and there's a formula due to Hadamard. So there's a general prefactor here, which depends on the viscosity of the object you have and the viscosity of the surrounding fluid. So this is we know how to compute this from fluid mechanics. Okay, so let me see. So how am I going to determine A? So I'm going to assume that the dynamics I write down will take me into an equilibrium steady state described by Gibbs-Boltzmann statistics. So if I look at the steady state, I'm not necessarily going to say in equilibrium, okay? I'm just looking at the steady state. What should I find if I calculate the expected value of Vt squared once the system's in equilibrium? What should I find there? That's right. So what you do is if you multiply by a half m here, right? We know that's equal to half kBt. Okay. Now let me see. Okay, so each degree. So basically we find that Vt squared is equal to kBt over m, right? So this tells us something about what we have to do. So let me have a look at this. So this is a nice calculation because it shows you how the stochastic calculus works. So let me have a look at. Let me have a look at V squared. So let me call Vt squared, let me call that S of t. This is what I want to compute, yeah? I want to look at the equilibrium statistic, I want to look at the equilibrium distribution of S of t. So let me have a look. Let me write down the stochastic differential equation for ds of t. So that's equal to dvt squared. So this is equal to 2 v of t times dvt, okay? plus, I have a factor of a half. I have to take the second derivative of v squared, so that will give me 2, and then this is going to give me yeah. If I use the Ito rule for the function s is equal to v squared. Okay, so this is equal to twice v of t. So now dv of t, where did I write the equation down? So it's equal to minus gamma times v of t plus a times db of t. It's not quite right, is it? Because it's m, I have to divide by m. Okay? Right? Did I save myself from being corrected there? I never divide by m. I give this, every time I give the lecture, I forget about m. M should be 1. Okay? And so that's the first term. And then I'm going to get a squared divided by m squared times dt, right? Because if you look at the noise term, dv squared, the noise term squared is just a squared dbt squared, and I've divided by m. Sorry? Oh yes, I always forget the dt's as well. Actually, that was a dt. I just forgot the d and the plus sign. Okay. Okay. Have I got everything? Good. Okay. So this is good. So let me have a look. So this is equal to. So actually, I have minus 2 gamma divided by m. I have vt squared here. So this is just s of t, right? Times dt. And now I'm going to get plus 2a divided by m v of t dbt plus a squared divided by m squared times dt. Okay? Now, so this is ds of t. And if you want, I don't really want to, but I can write v of t as the square root of s of t. I want. But that's the problem. I have a problem with the sign, so it's plus or minus, so it's a bit not very well defined there, right? But the thing is, I don't really have to bother, because what I'm going to do is I'm going to take the average of this equation. So the average value of ds of t is equal to minus 2 gamma divided by m times the average value of s of t. The term which was slightly embarrassing me here goes away because I'm taking averages, right? dbt is independent of v of t. And then I'm going to get plus a squared divided by m times dt. Now, if I'm in equilibrium, if I'm in the steady state, right, this guy is equal to 0 by definition in the steady state, right? No, nothing depends on time anymore. So this is equal to 0 in the steady state, assuming there is one, yeah? Not always the case. Okay, so if I say that this guy here is equal to 0, this tells me that the expected value of s of t must be equal to, have I forgot? I've missed out an m squared here, no? Okay. So this tells me that s of t must be equal to a squared divided by 2. The expected value of s of t is a squared divided by 2m gamma. Okay? Now we use the equipartition of energy. We know, so this is when we model, we always use, we could have non-equilibrium, we could have non-equilibrium forcing, things like this, but if we assume that the noise is there in the equilibrium system, okay, so I could drive my particle with a laser, right? And so the system might no longer have an equilibrium distribution. But if I say, well, the laser driving doesn't have any effect on the molecular noise due to the water, right? I can always do an equilibrium calculation in order to see what the noise should be, okay? Okay, so I can add extra things, but in the system, the water with my particle just diffusing around, this is how I have to choose the noise, right? It would be strange. Obviously, the laser might heat up the water, okay, so I might have to be careful there. But we have to, so you choose the coefficients in the stochastic differential equation in order not to violate the laws of thermodynamics, which we generally agree is a good thing. Okay? So when we look at this, this tells me that a half kBt, what is it? It's kBt. I said that S of t was kBt over m. Okay? So this tells me that A is equal to the square root of 2 kBt gamma. Okay, so we found what the... Okay, so this is an example of fluctuation dissipation theorem. Okay, you basically, if you have any sort of dissipation, some sort of friction, I mean, in order for your system to carry on doing something interesting, otherwise it would just stop doing anything, right? You need to have some sort of noise in order to have a non-trivial steady state. So this tells you that the noise, so you see it's proportional to the temperature times. Okay. Now let me just say a few words on, because it's, just go back. .7. So links with physical descriptions. Wow. I mean, this is a physical description, but so links with physical descriptions of diffusion. Okay. So actually, normally, when the first time you see that the diffusion equation, I don't know, normally they write down the diffusion equation for the concentration field. Okay, the concentration, it's not necessarily, so the concentration field, if you normalize it to 1, it's the same as the probability distribution, okay? So normally when you see a diffusion equation, normally you talk about Cx of t, which is the concentration of some diffusing species, right? So normally that's what you see. You don't talk about a probability distribution function, but obviously if I you know, I can make this look like a probability density function, right? Because I just take okay, so that looks like a probability density function. Okay, so you can talk about concentrations or you can talk about probability density functions. So if you have a system with no interactions, if I take some dye and I put it into a glass of water, you see that the dye uniformly equals the water if I leave it for long enough. Okay, it should do in principle. You can stir it to speed it up, but you find the equilibrium is a uniform state. Okay. Okay, so without interactions, okay, the steady state is C equal to a constant, right? Okay, so if you look at your glass of water, you put some dye in there, that's so you put a point of dye in there, eventually you see it diffuses out uniformly, okay? So the equilibrium, the system wants to go to a uniform state. So how does it do that? Well, phenomenologically, you imagine there's some sort of current, right? So the current, if you have a current J, okay, then you write down the equation, the conservation equation, is just that dc by dt is plus the divergence of J is equal to 0, right? That's not really a physics equation, it's a definition, okay, to a certain extent. So that's the first thing you write. And then the physics is, well, you say, well, if the system's uniform, it won't do anything, right? So if there are no concentration gradients, there'll be no flow of particles. So the current so you define it like this. You say the current must be proportional to some object D, which will be positive, times C. So it basically means if you have a region where the concentration is high, the particles will flow to where the concentration is low, okay? So this is particle flow. So this is like a linear response if you're doing so. So if I'm assuming that I've got some sort of isotropic system, if the gradient of C is 0, right, nothing happens, okay? And then you say, well, in principle, I could have higher derivative terms. So this is like a linear response. This is like some sort of weak effect. In principle, I could have higher derivatives of C. I could even have nonlinear terms, okay? But if I have no interactions, this is the simple law, and this is called Ficks Law. So it's a sort of phenomenological linear response, okay? And D is called the diffusion constant. Actually, D is strictly the, in this context, is the collective diffusion constant. Okay? So, so now if I put Ficks law into the conservation equation, I'm just going to find the dc by dt. Okay. Now, d in principle, if d is constant, I can put it out here, right? But in principle, d can be something which depends on the position in space, right? For instance, in a fluid, we saw that the diffusion constant depends on the temperature and the viscosity, okay? So in principle, this can depend on space, okay? It can vary. So you see, if you apply Ficks law like this guarantees that you have a uniform distribution. If I say that, if I look at the steady state, if I say this is a probability distribution, this equation is solved by C or P as a constant, okay? But this is an interesting thing, because if you look at there are quite recent papers where people get very excited about stochastic differential equations and the difference between Ito and Stratonovich. You see, because let me look at the stochastic differential. Let me have a look. What is this process? Okay. Now you might be tempted to say this is just free diffusion, right? So I have some sort of diffusion constant which varies in space. So if somebody tells me this, I might be tempted to write down the diffusion equation dx of t. So you see, you would take something like the square root of 2 of d times dv. Okay, so you have this. You have the factor of 2 because remember it's a squared over 2 here, right? So you might put that on the computer and simulate it, okay? Will you find a uniform distribution? So imagine I have some system where d varies, okay? Imagine d is big here. And here, what will happen to the particles? So the problem is if I take this process here, well, let's just say, is this the good equation? If you do this, the answer is no. You won't get the right answer. Okay, we'll come back and see why not. So if I write down the stochastic differential equation for this, so I can look at this, you see the diffusion equation, if I write the diffusion equation, it's dp by dt is equal to g. G is the generator of the diffusion times p, right? So g dagger is equal to, okay, as an operator, it's just takes the divergence of d and then it, okay, div d gradient, okay? So what's g? Who can tell me what g is? What's g? What's the adjoint of this operator? Yeah, this is g dagger. So if I take the adjoint of the adjoint, it gives me g back, right? But if I integrate by parts, okay, so if I just look at this, I have d. So if I put one function here, g, okay, if I do one integration by parts, it gives me, and I throw away the terms on the surface, I get grad g dot grad f times d. And then I do another integration by parts to make the f completely free. I have a minus sign when I do it the first time, right? Take this gradient here. And you can see that when I do it a second time with the gradient here, it gives me this, the minus sign goes away because I get another minus sign, and I get f outside and I get d grad g. Okay? So it's actually self-adjoint. Okay? Which is Not all the time are these operators self-adjoint. And I'm being told that my time is up. So for the next time, you can try and work out what is the correct, so using the fact that G dagger is equal to G, okay? Try and work out what the stochastic differential equation is and work out what equation you should put on a computer in order to get a uniform distribution, okay? You'll do it? Okay, any questions? Yeah, so actually, so the backward Fokker-Planck equation is the equation with G dagger. It's the equation with G dagger, and it's called the backward Fokker-Planck equation because it acts on the initial coordinate rather than the final coordinate, right?
Okay, so if there are no other questions, we'll meet again at 2:30.